Hello everyone again, and welcome to this particular video where in here we're going to be looking at the magnetic force on a current carrying conductor. And the better work for this particular video here is to first, our goal is to be able to derive the length of a straight wire magnetic force, and this is going to be followed by deriving the length of a curved wire in a magnetic field, and we'll have to derive that magnetic force and then apply a uniform magnetic field to wires that is actually either wave-like loop or closed-like loop. And now let's first look at all these various cases that will be applied to a specific set of wires. First is when dealing with a straight wire, and this straight wire is under the influence of a uniform magnetic field that is pointing away from this particular screen. We see three different setups right here, all with the same magnetic field that is uniform, pointing away from you in this particular screen. So first we see all these wires, which are the blue wires. We're going to look at case 1a, and in case 1a what we see is that there is no magnetic force because in here there is no current that is passing through the straight wire. Now what if you have a current that is pointing in the upward direction or moving upwards along that particular wire, and you have a magnetic field that is rightly perpendicular to that particular current? What we see here is that as the current moves upwards, we actually have a specific interesting bend in the wire that is pointing in the left direction. So the straight wire actually deflects to the left. And what if you have the other case in here when dealing with case 1c? And what we see in case 1c is that if you have the current passing downwards but you have the magnetic field that is pointing away from you, what we see is that our wire in general influences a direction that is pointing or deflects to the right. So based on this, we're going to look at various principles that governs these particular forces acting on the wire when the combination of the current and the magnetic field is applied to various particles in that particular wire, and how do those particles behave. So looking closely at the wire section, we actually see that if you cut out this particular wire and see how the particles, mainly charged particles represented as Q, is behaving when you have a current that is flowing and you have the magnetic field that is pointing in that direction, and you have in here, as stated before, the current moving in the opposite direction to that of the particle movement, charged particle movement. What we see is that the particle moves with a drift velocity, and since we have one charged particle's magnetic force in here, which will be determined by multiplying the quantity of charge by the cross product of the drift velocity and the magnetic field, we therefore, to determine n number of charged particles in that particular segment of the wire, we just have to multiply our n in here. In this case, n could be how many Q's here? We have 3 Q's, or it could be 4 Q's, but all of them will be influenced by that same drift velocity in that same magnetic field. Therefore our n will be multiplied by the quantity of charge and the cross product of the drift velocity and the magnetic field. So this is a way to determine the magnetic force that is acting on any n number of charged particle in a specific segment of that particular wire. So looking at this, since we know that n is the quantity of charges in that segment, therefore n is equal to the little n, where little n tells us the number of charges per unit volume. So in here we're going to introduce volume in here, where our area is that specific cross-section of that particular wire, and we're going to also take into consideration multiplying A by the length of that particular segment, which is represented as L. So this kind of looks like a cylinder-ish in a way, but we're going to deal with this in terms of just A being the cross-section area where those charged particles occupy. So in here we're going to put this expression for the big N, which is number of charges in the segment, in equation 1. So equation 2 is going to go into equation 1, and as a result of that we will have a new expression for the magnetic force to be equal to the quantity of charge times the cross product of the drift velocity and the magnetic field, all multiplied by the number of charges per unit volume multiplied by the cross-section area times the length of that particular segment cut out. So since from the Ohm's law we know that the current is equal to the, in this case, number of charge per unit volume times the quantity of charge multiplied by the drift velocity and the area, we will have to put this in place of those variables in the force magnetic field in that equation, and we will arrive at a new expression, which is the general formula to determine the magnetic field force that is acting on that wire when a current is passing either upwards or downwards, and a magnetic field is actually influenced in that particular wire, and we have to consider in this case the length of that particular wire. So in this case the current is multiplied by the cross product of the vector, which is the length of the wire, which is in the same direction as that of the current, and the magnetic field in that particular case right there. So in here, since we have arrived at the validity of this particular expression in terms of the cutout conclusion for a straight segment wire, which is the cross product of the of the length of the wire and the magnetic field, all multiplied by the current, which gives us the force. Take note here that the length vector is actually in the direction of the current, and in this case for a straight wire, since we have this particular wire which is expressed as this blue line, we have the magnetic field that is pointing rightly almost perpendicular to that of that wire length, and once you have that current passing through that particular wire, it means that this angle, which is represented as theta, will have to be influenced by the relationship with the length of the particular wire. So therefore, since we have the unit vector for the magnetic field combined with that of the length of the wire, we will arrive at a force that is pointing upwards. So therefore, in this case, since the magnitude of that particular length of the wire vector is equal to L, which is the magnitude, and if the particular length vector is actually perpendicular to the magnetic field vector, therefore in this case we can actually determine the magnitude of the force vector, which is equal to the current times the length of the wire times the magnetic field, all multiplied by sine 90 degrees, since we made a condition that the length of the wire vector is perpendicular to the magnetic field. Therefore, in this case, the force is ideally equal to the length of the wire times the magnetic field multiplied by the current. So, since we have that conclusion being made for a straight wire that is influenced by a magnetic field that is perpendicular to the length of that wire. What about case 2 when you are given a curved wire in a uniform magnetic field? And there are some things we'll have to consider in here. We're going to consider the derivative of the speed of a particular particle with the cross product of the magnetic field. But how are we going to be able to determine that combination? In here we have a specific curved wire, and what we see in this curved wire is that it is under the influence of a specific magnetic field, and this magnetic field, once you pass current across that particular curved wire, this actually shows us that the behavior of the particle, in this case, as the particle is moving, the particle, one of them is actually moving at the derivative of that particular speed, which is represented as ds with a vector right there. So therefore, in this case, looking at closely at the vector component, we see that we have the magnetic field vector, and is combined with the velocity or speed derivative of that particular one particle or charged particle. Therefore, the force is actually pointing towards this particular screen or towards you. So in this case, the derivative of the force is equal to the current multiplied by the derivative of the speed of that particle cross product with the magnetic field. So therefore, in this case, the force vector is equal to the current multiplied by the point from B to A, which is the starting point of that charged particle, to the end point of that charged particle. But in this case, we are doing the integration of point A to point B, and we see that this location where the particle starts to where it ends on that particular wire, taking the integration into consideration, gives us the impact on the derivative of the speeds of that particle, and the cross product will be applied to the magnetic field. So therefore, this is how you determine a curved wire that is actually under the influence of a uniform magnetic field, and this is how you are able to determine the magnetic force of that particular curved wire. So since we have this expression, we notice here that you need to perform the integration in this particular case in order for you to arrive at a curved wire, because it is not a straight wire. So a straight wire where you're not performing integration, a curved wire, this is where you actually perform the integration, because in here you're looking at the starting point to the end point, and there is all these considerations because of the concavity of that wire or loop that influences, or that is influenced by the integration of the varying speeds in there. So since we have this actually taken care of, we actually are able to consider this formula in this case for a curved wire. So once we have that as a starting point, now let's look at case 2a, where we have a curved wire in a uniform magnetic field, and in here we're going to see how we can go even further into actually looking at a curved conductor. And a curved conductor, in this case, we actually see that the force is equal to the current multiplied by the integration from point B, or from point A to point B, of the derivative of the speed of that particular charged particle. And once you're able to arrive at that integration, you must perform the cross product to the magnetic field. And once you're able to do that, we need to know that in this case, the integration of the speed actually is equal to the length vector's derivative. So in this case, this derivative is actually in the direction from point A to point B. So once you're able to have this equivalence derivative to the integration going from the speed to the length of the wire, we therefore can determine the force vector or magnitude to be equal to the cross product of the derivative of the length of the wire and the magnetic field vector, and this will multiply by the current that is passing through that particular wire. Therefore, this is a way to determine a curved loop conductor magnetic force that is applied to a current carrying conductor that is curved in nature. So once we have this, we're going to look at the final case here, where what if we want to generate a zero force, and how do you generate a zero force in a specific wire construction that is influenced by a magnetic field. So what we see here is that for we to create a zero force, can you guess? We actually have to perform a complete loop where you have a closed wire system that is under the influence of a current. So once in this case you are able to create a closed system, it could be a pentagon that is closed or a polygon that is closed, as long as current is passing through and is going in a circular path, there is a zero displacement that results in a zero derivative or integration of your derivative of the speed. Therefore, since there is no starting point and an end point, because it is circular in terms of the wire construction, we actually will create a integration from point B to A, which in this case there is no B to A, but it's just a loop symbol, where in here we actually have a symbol in here to be a knot that is between the integration sign applied to the derivative of the speed. Therefore, this here, if we perform the cross product to that of the magnetic field, we actually say that in this case, for a set of displacement vectors forms a closed polygon. In this case, this is actually equal to 0. Therefore, the total magnetic force on any closed current loop, don't forget that, in a uniform magnetic field is equal to 0. Therefore, if you put 0 into your force vector equation, it means that 0 is multiplied by current, which is 0, or sorry, you start with 0 multiplied by the magnetic field, which is equal to 0, but 0 multiplied by the current is actually equal to 0. Therefore, the force magnetic is actually equal to 0. So in here we've seen different cases and how all these different cases, either being a straight wire or a curved wire or a complete closed loop wire, influences the force that is generated. One being for a straight wire, all we just have to do is do the cross product of the length of the wire and the magnetic field, multiply that by the current to give you the force. If it's for a curved wire going from A to point B, we just have to do the integration from point A to point B of the derivative of the speed of that particle, do the cross product with that of the magnetic field, and multiply your answer by the constant, which is the current, and that will give us the force. However, if you have a complete closed system or closed loop, which is either in the case of a polygon, we can actually determine the force to just be equal to 0. Why is that the case? Because the particles they don't have a displacement. The displacement in this case is equal to 0 because it is in the circular path. So that is about it for this particular video. Hope you're able to understand these magnetic forces on a current carrying conductor. Please hit the comment down below. Let me hear your thoughts. By that way, I can talk to you all soon. Stay smart and always believe in yourselves.